Some important properties. Given that A is n by m and B is m by n, the determinant of In plus AB is equal to the determinant of Im plus BA. What is In or what is Im? This is identity matrix which belongs to Rn by n. In other words, it's a square matrix of n by n. And identity matrix means that everything is 0 except main element, which are all 1. And this one is the identity matrix which is belonging to m by n. In other words, it's a square matrix of m by n. And we understand that A multiplied by B is n by n, B multiplied by A is m by m. But the thing is that the determinants are the same. If m is equal to 1, in other words, if A is a column vector and B is a row vector, then the determinant of In plus AB, look, a column vector multiplied by a row vector will become a square matrix, right? And now we have In plus AB, which is a matrix. We want to find its determinant. This is equal to 1 plus simply BA, because BA is a scalar, and you just add with number 1, and then you get the results. So this will be very useful, especially if, let's say, A is like 10 by 1, B is 1 by 10, so the result is 10 by 10. Now you're adding the identity and you want to find its determinant. It's time consuming, it's not easy. Whereas multiplying element-wise of B and A, get one scalar, add 1, find the determinant will be very easy. And if In plus AB is non-singular, in other words, if this determinant is not 0, we can actually calculate the inverse. And the inverse is this. In plus AB inverse is In minus A multiplied by In plus BA inverse multiplied by B. One very tricky, okay, finish that one. Then I will ask a very tricky question. Okay, are you ready for the tricky question? And the tricky question is that, given that A is n by 1 and B is y by n, okay? A is a column vector and B is a row vector. And we know that A multiplied by B is a matrix. What can we say about the inverse of AB? What can we say about the determinant of AB? And because if we know the determinant of AB, we can calculate the inverse of AB. We know In plus AB. AB is a matrix. The question is, what is the determinant of AB? Or do we have a very shortcut of calculating the determinant of AB? It's very good for early morning, the brain starts to work. It helps us not to get the outside. I give you a hint. Go to the properties of determinant and look at the general form of the third properties that I wrote. What was the third properties, the general form, Ike?
Universal matrix.
The determinant of a matrix, what?
The inverse of this one.
No, determinant, you are in the inverse. Go back. Yes, the general form, read it please. Loudly.
The two rows or columns of the matrix are the same, then determine that A is equal to 0.
The general form, next sentence.
If a row or column is the result of linear combination of the other rows or columns, then determine is 0.
Okay, cool. If rows or columns of a matrix is a linearly combination of the other one, the determinant is 0. So let's look at this one. I'm erasing here. Let's say A is A1, A2, A3. My bad. Is A1, A2, A3. And B is B1, B2, B3. Look. AB is A1, B1, A1, B2, A1, B3. Then it's A2, B1, A2, B2, A2, B3. Then it's A3, B1, A3, B2, A3, B3. Look. First one, look, this is the first one. The second one is the first multiplied by B2 divided by B1. Isn't it? And this one is, first one is B3 divided by B1. Which means that the first one, the second one is actually the linear combination of the first one with itself. Because it's simply multiplied by a constant. And based on the third property in the general form, the determinant of this matrix is 0. The determinant of this matrix is 0. So, then my question, which was, what was my question? Did I write it? If we have a row vector, and if we have a column vector multiplied by a row vector, the determinant will be 0. So what is the inverse? It doesn't exist because it's not. It's a singular matrix. I mean, the conventional inverse does not exist, right? Because we will talk about a general form of inverse, which we can calculate the inverse of everything. We don't care. But the conventional, the traditional inverse does not exist simply because it is a singular matrix, and this is the proof. So X, I think I remember on the previous session when I wrote that X, Y transpose is a matrix, I said that this matrix is a singular matrix. This matrix does not have an inverse. And the reason is because of that property. Okay? Now, what about here? What happened? How do I guarantee that this exists?
A and B are not, A is not inverse of B.
Can it be? Does inverse of A exist? the conventional inverse does not exist. Why?
It's a vector.
Yeah, it's not a square matrix, so the concept of inverse is not valid. Now, this one, we are kind of in the secure form because we know that AB, the determinant of AB, we know that is 0. We know the determinant of AB is 0. But what happens is that I come and I add 1 to this, 1 to this, and 1 to this. So I destroy this, I destroy this. Can I come with an example which actually after adding these ones, still I am kind of linearly combined? Maybe yes. Maybe yes. Because this doesn't mean that the result is not a 0. The result might be 0 because b multiplied by a might be minus 1. We don't know. But in general, if we are adding, if we know that AB is like linearly combined, the rows are linearly combined, adding 1, not onto all rows or columns, but like on a diagonal, with high probability will destroy whole this concept of being linear, generally. But again, you can come with some counterexamples. Okay?
Sorry, so you said the determinant of AB here is 0.
Yes. We just proved the determinant of AB is 0.
Okay, yeah.
But when we are adding now, look what happens is that I am adding 1 into here, 1 into here, and simply I can understand that this term that I have written here is not correct. So, let's write a few more these block matrix operation formulas, which will be kind of useful, and it is this. For aforementioned block matrix, the block matrix that we described before, the matrix inversion lemma is A plus B D C inverse is equal to A inverse minus A inverse B D inverse plus C A inverse B inverse C A inverse. It says that the inverse of this matrix is this. Prove it. How do you prove the inverse of this is this? Do you know any easy method?
Multiply them.
Well, I multiply both sides by this term. What is this? This is I. So let's see if I have A plus BDC multiplied by A inverse minus A inverse B D inverse plus CA inverse B inverse CA inverse is I or not. It's pretty straightforward. In a couple of lines you can simply just expand this multiplication and you see that this is actually I. Well, easily you can see that A multiplied by A inverse, this is the first I, and then we have this term multiplied by this, and this term multiplied by the whole of this. And then you will be able to factorize this term out, and you see that easily we will get to the I. Okay? Do this one at home. It's a good exercise of remembering how to do this neural manipulation. But remind me, next lecture I can solve it on the board. As I say, just a couple of lines. Now, in order to be able to find those distributions, let's go over a few more useful terminologies. Again, remember, you don't need to memorize any of these things, right? Because they are always in front of you. The important thing is that you might need to know when you need to use them. Like maybe it will be easy somehow replace this term with this term in order to do the calculation. More important than this course, in the real life, when you are doing your work, when you are doing your research, you need to be able to know that, okay, some of these ones are kind of equivalent to each other, so you can replace them, or you can easily calculate some other things based on their application or the research that you are doing. Because as a reminder, in the examination, we know that it is open book, open note, and even open computer. Simply because I don't want you to memorize anything or be worried of numerical calculation. Okay. Now, some more useful terminologies. The first thing is complex conjugate of a matrix. If I have a matrix where it belongs to C n by m, so it's a complex number. And if I say that this matrix has been conjugated, what does it mean?
Transpose the node terms conjugated.
No. If you want to transpose and conjugate it, I would say that is conjugate transpose. I'm just saying only conjugate. What is a conjugate? Do you remember what is conjugate in complex number? If Z is A plus IB, which is or plus minus IB, which is a complex number, the conjugate of Z is A minus plus IB. So if we have a matrix and we are conjugating, it's just like that all its elements are conjugated. Nothing will change on the rows or columns, only the numbers will be conjugated. What is the conjugate of 2 minus I?
2 plus I.
2 plus I. What is the conjugate of 5.3?
5.5.
5.3, because a real number's conjugate is itself and only conjugate effects on the imaginary part. Now the next thing is the transpose of a matrix. How do we calculate it? A transpose is exchanging rows and columns. So it will be A instead of IJ, let's say JI. Keeping the notation that I is row, J is column, so we are just changing the rows and column. Now, the next thing is Hermitian transpose, or in old fashioned we call it conjugate transpose. Conjugate transpose. We show it as A H or A star or A conjugate transpose, and it is simply all the elements are conjugated and transposed. If obviously A belongs to R n by m, A Hermitian is equal to A transpose, because a conjugate transpose, the conjugate of the real number is itself, so conjugate won't do anything, so the transpose is only affecting. A plus B Hermitian. Now, we use this conjugate transpose because whatever we do here is also valid for the transpose. So if I am adding two matrices and the result is conjugate transpose, what can I say? It's just like each of them are being transposed and then added. What about the multiplication? We are adding BH multiplied by AH. We have to change the positions because otherwise the multiplication might have a problem. If A is an S-square complex matrix, then we have a few important terms. The determinant of AH is equal to the determinant of A conjugate. Can you tell me that what is the real term? Like if A was an S-square real matrix, how can I write this one? If it is conjugate, if it is complex, A Hermitian is equal to A conjugate. The determinant of A Hermitian is equal to the determinant of A conjugate. But if A was R in R, if A is an S-square matrix of real numbers, how can I simplify this number, this formula?
I suppose
Tell me, what is the conjugate in case of real numbers?
it's the same number.
Sorry?
Transpose.
Conjugate.
It's the same.
Just the same. Just the same. So in the right side is just the same. Here we have conjugate transpose. What is it in the real form?
Transpose.
Only transpose. So the determinant of A transpose is the same as the determinant of A. Or in the very general form, the determinant of conjugate transpose of A is the determinant of conjugate of A. Another thing is that A conjugate transpose inverse is equal to A inverse conjugate transpose. And if I am multiplying my matrix with a constant C, which is obviously C belongs to C, it is equal to, I can put, so CA is a conjugate transpose, I can put the constant out, but I have to conjugate it, multiply by AH. A few famous definitions. Bless you.
Thank you.
You may recall them. What is a symmetric matrix?
Matrix that is identical to its transpose.
It's transpose. Very good. A is equal to A transpose. And SQ symmetric. A is equal to minus of A transpose. And Hermitian and SQ. Hermitian, now you might be able to kind of generalize what they have above. What do you think if the Hermitian matrix is?
Same properties for.
Okay, don't let me say. Tell me what it is.
A is identical to its Hermitian transpose.
Excellent. And the SQ is? Now, do you have any question? But I have a question, if you don't. Can I first learn your name? I know Andres, I know I don't know what's your name?
Hassan.
Hassan?
天豹
Tim Bao. Can I have a
Just
short form?
just 豹
Pao.
yeah 豹
Bao.
yeah
Bao. Cool.
Preet.
Preet?
Laura.
Now, I thought you cannot attend the Friday classes.
I could today.
Oh, okay, today. Okay. What was your name you said?
Laura.
Lau, okay. Lau Joost, right? What's your last name?
Joost.
Joost, my bad. I turned you into cheese.
Don't worry, it's common.
Yeah, you cannot pronounce mine anyway. Now, okay, now that I know the names, maybe Hassan will tell me what is the, if I tell you that the matrix A is Hermitian, what would be your observation? What would be your conclusion? What do you conclude? Definitely, then A has this property.
Since Hermitian exists.
Hermitian means that A is equal to A conjugate transpose. Think about it, that what can you conclude? Like, then A has this specific property. And meanwhile, Preet will think of, what about if it is a SQ Hermitian? Then what can we definitely say about A? The backup of Hassan is I, and the backup of Preet is Bob. If I tell you that A is like that, what can you strongly and correctly say about A? Anyone, any comment? Yes?
Square matrix.
Then the same conclusion comes from a skew matrix. And this conclusion can come for many other matrices. Like for A is equal to A transpose and so on. But there is something very strong. Okay, let's look at it from this perspective. What is this operator?
huge
What does it do?
transpose
Conjugate and transpose. If I am, we understand that it should be a square matrix because the size should meet. So Laura, if I am transposing my matrix, which elements are not changing? The main diagonal elements are not changing. Look, I am transposing my matrix, the main diagonal are not changing, they are sitting on the same place. I am conjugating them and they are not changing also because they have to be the same. Then, can you tell me that what type of numbers can be conjugated and they won't be changed? Real numbers. So main diagonal are real numbers. Must be real number. Because I am conjugating it and they are sitting in the same place and they should not be changed. Right? So knowing this one, what is your conclusion regarding to the SQ Hermitian? Main diagonals are sitting in the same place. I am conjugating it, but everything will become negative. I mean, not necessarily negative, it will become opposite sign.
0, 0.
0 has opposite sign? No, cool, okay. Actually, 0 is a real number, so. You wanted to say something about?
We're thinking the diagonal is equal to the reverse and to the inverse of it.
No. There is no concept of inverse. Look, yes.
All elements are complex.
No, I know what you want to say, but you choose the wrong word.
Maybe they are all imaginary.
All imaginary, exactly. All imaginary, because they must change the sign. We know that integers are not, reals are not changing anything. So this one, there should be no real part. If there is a real part, we understand that when we are conjugating it, the real parts will stay the same. 2 plus j will become 2 minus j. The 2 is not changed. So, for us to guarantee that the signs are being changed, it means the main diagonal must be imaginary. So, main diagonal must be only imaginary. We know that if z is equal to a plus ib, I is the imaginary unit, this is called the real part, this is called the imaginary part, and the whole thing is called complex number. Okay? So this is a very important conclusion that we can get. And actually, we can consider the concept of symmetric and SQ symmetric. Let's go to the real as even and odd. Do you remember even and odd functions? Do you remember even and odd function? What is an even function?
Symmetry.
Symmetric around the y-axis. And the odd function was asymmetric, right? Around the origin, like the sun. So, symmetric means even, like even, SQ symmetric means like odd. And we remember in the mathematics that, in calculus, that every function can be written as addition of an even and odd function. In other words, any matrix can be written, talking general, any complex matrix can be written as addition of a Hermitian and an SQ Hermitian, or an addition of a symmetric or SQ symmetric matrix. So this is what we want to write. Every Hermitian matrix can be actually written as A is equal to C plus J D, where C is symmetric and D is SQ symmetric. Remember, we are using the word symmetric and SQ symmetric, which means that C belongs to R n by m, D belongs to R n by n. They are not complex number. The additions results into the complex number, but C and D are real numbers. Now, this is for the Hermitian. What about the skew Hermitian? Every skew Hermitian matrix can be written as A is equal to C plus JD. A is equal to C plus JD. What can we say about C and D? Where C is skew symmetric this time, and B is symmetric. I'm not erasing everything in here because I want to use some of these properties. If A is Hermitian, then the determinant of A is, and A inverse is. Now, what can we say about the determinant of A? The determinant of A will be real. And what can we say about the inverse of A? It will be also Hermitian. There are a few more terms to discuss, like what is a unitary matrix, what is a normal matrix, and what are the, like we talk about the for